Hello, I'm Eamon Kyo of the University of California, Riverside. Thank you for watching my talk. Before I begin my talk, I want to make some disclaimers. I'm going to be making some unflattering claims about academic research in anomaly detection. I want to point out that these are my ideas and not those necessarily of my students or UCR in general. And of course, I'm not claiming that my research is free of these flaws or flaws in general. I also want to apologize that these slides are a little bit wordy, but I do hope that people will read these slides offline also. Okay, let's get right into it. My overarching claim is that most papers on time series anomaly detection, or TSAD, have one or more flaws. And because of these flaws, we cannot trust these papers. Essentially, they make no contribution. These flaws include this one here, perhaps the most important one, which is a test on deeply flawed datasets, and any claims made upon these datasets themselves are untrustworthy. Let's get right into it. So of course, some papers only test on private datasets or synthetic data. And I'm simply going to ignore these for this talk. I think this paper should be ignored in general. But the rest of the papers test on a handful of benchmark datasets created by Yahoo, Nementa, NASA, and so forth. So let's zoom in on these datasets and see what the problem actually is. Let's begin by looking at this dataset, possibly the most famous dataset in this domain. It's called the New York Taxi dataset. It represents the taxi demand in New York over about 6 months. And it's claimed that there are 5 anomalies here: New York Marathon, Thanksgiving, Christmas, New Year's Day, and a blizzard. That seems plausible, but let's think about this for a moment. I actually claim that there are many, many more anomalies than this. For example, there's clearly an anomaly, if you like, for Martin Luther King Jr. Day, for the Black Lives Matter March, for Comic-Con, for Climate March, and so on and so forth. So given this, what do you make of a claim like this? This paper claims to be better than some other method because it got a tiny fraction of percentage more correct or higher F-score. But if half the data itself is mislabeled, what does this tiny difference actually mean? Once you understand these data sets are mislabeled, you begin to see that many claims made in papers are very, very, very strange. For example, this paper here claims to have perfect precision and recall on this data set. But once again, if half the data is mislabeled, what does it mean to have perfect precision and recall? What it means, I think, is overfitting. Here's another famous data set called Yahoo, and this is one of the sub data sets. The black time series here is the actual data, and the red binary vector here is, of course, the label. So this is plausibly an example of an anomaly here, and an anomaly here. This anomaly C here, I've zoomed in below, and the actual anomaly, of course, is this little dropout you can see right here. But if you take a second to look at this data more carefully, what you'll see actually is that there's another example here, which I've labeled D. If I place D on top of C, you'll see actually it's virtually identical. It has the exact same dropout. So if that's true, why is D not an anomaly and C is? And the answer is, of course, simply that it's mislabeled. Here's another example. This time it's only a subset of a time series that I can zoom in on. But here we see that the section labeled here, A, is an anomaly, but B is not. So if you predicted this location here on A, you would get a point or a score. And if I predicted this location here for B, I would not. But look at this. Literally nothing has changed between A and B. So how can you say that A is an anomaly and B isn't? It's simply a mislabeling. This mislabeling really matters. So look at this paper here. It's tested on this data set from NASA, and it's claimed to be better than its rivals, 3 of which it beats by only about 3%. However, the amount of mislabeling in this data set is at least an order of magnitude greater than that. Let me show you one concrete example. On this particular data set, it's claimed the only anomaly is in this location here, which I've marked here in pink. But if you visually examine this, it's very obvious there are two near identical extra anomalies here and here, which I've marked in green. So once you understand this, these numbers with 4 significant digits really make no sense whatsoever. I could do this all day. There are lots of mislabelings in these datasets, but in a sense, actually, it's almost a tautological claim. In fact, you can never have perfect ground truth for anomaly detection. It's logically impossible. Let me explain what I mean. So for some machine learning problems, we can get perfect ground truth. It is logically possible to get 1 million photographs of cats and 1 million photographs of dogs, and that's 100% correct. But for anomaly detection, that can never happen. Let me explain why. Look at this data set here, which is used by many, many people. And you'll notice actually that here, instead of having 5 bumps for 5 working days, there were only 4 bumps. So Friday was a holiday, and many people have said that is an anomaly, and that seems perfectly reasonable. But let's think about this. Suppose we interview people at the factory and ask them for their opinion. It might be that Joe says, no, Friday's not an anomaly because that happens every year. The real anomaly actually happens to be right here when they had a flood and they turned on the emergency pump. And if you ask for Susan's opinion, Susan says something different altogether. She says the anomaly actually happened over here, the high frequency noise, due to the use of a TIG welder. And of course, Tim says something different, and so does Bick, and so on and so forth. My point is, we can never, ever possibly know all the out-of-band possible causes for anomalies. We can never really be sure what we're seeing actually is a true false positive or a true false negative, and so on and so forth. And just given that one fact, it's simply nonsense for papers to publish results with 4 or 5 or 6 significant digits when there's so much inherent uncertainty in the data itself. The benchmark datasets have additional problems. Another really important one is triviality. I claim that most of these benchmark datasets are simply too trivial to solve to be interesting. To make this claim more concrete, I need to define trivial. Here's how I'm going to do it. A time series anomaly detection problem is trivial if it can be solved with a single line of standard MATLAB, or Python, or what have you. And of course, we cannot cheat by basically calling complicated functions like k-means. We have to simply restrict ourselves to the kind of plain vanilla MATLAB code. Let's see this. Here's a data set from the Omni benchmark. It's been used in dozens of top-tier papers. Here's one of the time series, and here is the binary ground truth that labels 2 anomalies here and here. But I can actually solve this using one line of code in multiple ways. This works, and this works. So again, my claim is, if I can solve this one line of code so simply and so quickly, is it really a worthy problem of investigation? Here's another example, this time from Nementa. Once again, we have a time series, we have the ground truth, and once again, very quickly, one line of MATLAB code, I can solve this and get the same ground truth. Here's another example from Yahoo. It's a noisy, complicated data set. Here is the anomaly, and here with a few lines of, actually a few ASCII characters, I can get exactly the same result. And actually, let me zoom in here. This actually is 2 anomalies, one following the other very quickly. But again, if you look at my little one line of code here, it exactly predicts the correct answer. Here's a paper that looks at some spacecraft from the NASA dataset, time series. And here they show the original data and the original labels. There's an anomaly here, here, and here. And they run a very complicated algorithm. At the end of that, they find the 3 true positives, and they get 1 false positive here, a pretty good result. However, once again, with a tiny bit of MATLAB code here, I can get the exact correct ground truth. Here's an example from the Omni benchmark. This is a multidimensional data set Let's just look at one dimension, in this case, trace 14. Here is the time series data, and here in red we see a binary vector with all the labels. Once again, on this data set, I can actually solve it with a single line of code. And in this case, a single line of code is basically statistical process control, which is about 80 years old. If you're not convinced by the one-liner argument, I'll point out that techniques from data mining from 20 years ago will actually do all these problems too quite well. So here's a Yahoo benchmark, here's the ground truth, and here's a 20-year-old simple, fast, parameter-free idea that finds the right results. So philosophically, what does this one-liner argument actually mean? I could have cast it in more rigorous terms, like chomograph complexity and so forth. That seems a bit pretentious though. Let me put it the following. Here are some problems people have actually studied in machine learning and made some progress on. Suppose I told you I could solve one of these problems. Let's pick this one here, of determining if a text review of a product is positive or negative by looking at the text. And I could do this with one line of code. You would be suspicious, and you should be suspicious. And you might investigate the data and find out, oh, I could do this in this case only because the positive reviews are all in uppercase, but the negative reviews are in lowercase. So yes, I could succeed here with one line of code, but really it was a trivial thing. My success here says nothing about the ability to classify text in general. This is exactly what the one-liner argument is saying. If I can solve a problem with 5 seconds of introspection and one line of code, then the task itself has some trivial structure, and it really wasn't worth investigating in the first place. So to summarize this section, at least 90% of the benchmark data sets that I've seen can be solved with simple methods dating back many decades or with trivial one-liners. In addition, 90% of the benchmark data sets can be solved without needing to even look at the training data. And that should be worrisome. If people are doing machine learning or deep learning, that implies you to look at some data from which to learn. If you can solve these problems without looking at any training data, in what sense do you need learning? In what sense are you doing learning? The benchmark datasets have lots of additional problems. Here are some examples. If you actually look at where the anomalies occur, they often occur towards the end. This kind of makes sense because often machines are run to failure, and by definition, the anomalies appear at the end. So for the Yahoo datasets, here's a histogram of their occurrences, and you can see that actually most of them appear towards the end. However, this is actually the problem, because any algorithm that simply guesses the anomaly is near the end will tend to do very well, much, much better than the default rate. Another problem that we see is unrealistic anomaly density. So here are some examples from NASA, and you can see actually that more than half the data is anomalous. And that just strikes us as being very, very, very strange. Anomaly is in a sense a synonym for rarity, but clearly here anomalies are not rare, they're more than half the data. Any real anomaly detection algorithm must be able to deal with the tiny probability of seeing an anomaly. And when you have data like this, you simply cannot learn that. As an aside, notice this dataset also has run to failure bias, triviality, and almost certainly some mislabeling. This is really a worthless dataset, and you really can't trust any results upon these datasets. Here's another more subtle example. This is a dataset, this is a snippet of it, and it has 133 anomalies. However, these anomalies are all basically identical, as you can see here. So first of all, is this really anomaly detection? Isn't it much more similar to classification or clustering? If you find a single anomaly here, since they're all basically identical, you're going to find them all. And so if you report something like, well, we got 133 out of 133, that implies some wonderful success, but I would argue you really got 1 out of 1. I'll also point out in passing, this is also a very trivial data set in the sense of one line of code to solve. So to put this in context, here's a quote from someone, Mike Noskov, who actually does anomaly detection for a living in the oil and gas space. And he says this: in his world, one anomaly a year, that's not good. If you have 2 anomalies in a year, people start talking. And if you get 3 anomalies in a year, you better start looking for a new job. You're going to be fired. So the idea that you have, in some sense, 100 or more anomalies in 5 minutes that are all identical just doesn't make sense. This is not the real world. Let's consider an additional problem in TSADI papers: spurious precision. Many papers report 3, 4, or 5 digits of precision for experimental results. And of course, as we've already seen in this talk, the great uncertainty in the ground truth labels suggests that actually is not very meaningful. But it gets worse than that. Even if it is assumed we had perfect ground truth labels, much of the precision claimed would still be wrong. Let me make that clear. So here we have a data set that's sampled once an hour, and it happens to be the case that the sensor was broken between midnight to midnight on Christmas Day. So suppose your algorithm actually runs and it finds this anomaly. Can you claim you got 24 out of 24? The answer, of course, is clearly no. These are not independent events. You should report you got 1 out of 1, not 24 out of 24. Now, that might be obvious to you, but it apparently is not obvious to a great many TSADI papers. Let me show you some examples. Here's a paper that tested on this data set. And to be clear, this is the entire data set plotted on the screen, not just an excerpt. And of course, the anomaly is right here. It's a very trivial, obvious anomaly. Now, a recent paper did some tests upon this, and based upon that, they produced this table here, which has a bunch of numbers with 4 significant digits. But of course, that's completely meaningless. At best, you get a single binary number out of this: true, false, you found the anomaly, or you didn't. It's not logically possible the position here corresponds to timing, because that would correspond to a timing down to about 1/250th of a second, which is medically meaningless and impossible. This is a big problem. A great many TSADI papers make these claims with lots of significant digits, which kind of implies some kind of wonderful distinctions being made here. It's simply nonsense. This paper has that problem and an additional problem. Many papers have non-reproducible experiments. What they actually do is they give away data sets publicly available, but the labels they use are not available. And of course, that means you cannot reproduce a single number. If I'm being more cynical, this is open to an obvious idea for abuse. You could actually run your algorithm on the data first, and then use its predictions as the ground truth. Then, of course, you can test your rivals on your ground truth, and they will do worse than you will, by definition almost. So here's a data set, and they test on these 2 particular data. So here's a paper. They test on these 2 data sets, 2D gesture and power demand. Now, as it happens, I know these data sets very, very well because I introduced them to the community about 20 years ago. And in particular, for 2D gesture, it actually corresponds to a video of me and my student. And so because it's me and because I still have the video, I know this data set better than anyone else in the world. And what I can say is this data set is okay for maybe an anecdotal example. And maybe you could get from this a single binary number, true or false. But the idea you can get an entire table of 4 significant digit numbers is completely nonsense. There's simply no logical way these authors could have pulled out this kind of ground truth here to allow this kind of significance. This is just nonsense. An additional problem that's pervasive is assuming that deep learning is the answer to TSADI problems. So a large fraction of papers assume this, and the paper kind of reduces to something like, we'll show that this variant of deep learning is better than those other versions of deep learning. However, because of the many reasons I've discussed above, I believe there's actually currently 0 evidence that deep learning works well for TSADI problems. And we should actually think that it would have difficulties. Deep learning often works well with lots and lots of labeled data, but in TSAT problems, there are few or no labeled examples. Moreover, deep learning tends to be very complex, and TSAT problems often have relatively small data sets to begin with. If you look at the problem of time series classification, which is different to, but in some sense similar to anomaly detection, this is the best case for deep learning. It has lots of labels, lots of data, lots of constraints in domain knowledge, but even there, deep learning is only a tiny bit better than simple 50-year-old nearest neighbor classification with, say, dynamic time warping. So to be clear, I'm not saying deep learning could not work with TSAT problems. However, I'm absolutely convinced there is no currently published evidence that shows that it really is better than these decade-old approaches. Let me make this clear with a simple example. This is one of the best papers I've read on deep learning for TSAD. It's a nice paper, well written, good reproducibility, some nice insights. At the end of the day, however, this is what one of the datasets looks like, and here is the ground truth labels for it. However, this is a 20-year-old algorithm that's very simple with one parameter, and as you can see, actually it works beautifully well in this problem. So there's simply no evidence in this case, for example, that deep learning gets anything useful for us, and this is more generally the case in all the papers I've read so far. I want to give you an example that's a little bit different, but exemplifies the problems of using deep learning. And the problem is deep learning, but shallow thinking. So at least 2 recent papers in classification did the following. They used deep learning to look at a PPG signal. That's the blood oxygen concentration you get from these little finger sensors, for example. And then they classified the person's behavior into, let's say, walking or running. This actually is a surprising result, right? Obviously, with accelerometers or gyroscopes, you can actually look at movement and figure if a person's walking and running. But doing it for this PPG signal seems to be quite strange and amazing. And both papers say it's because of these kind of magical attributes of deep learning. However, let's take back a step and think about this more carefully. If you have PPG, then you can easily get both the heart rate and the respiration rate. And we've known that for decades. Let's say I do that directly, and I simply plot the data into a 2-dimensional space based upon those 2 features, the heart rate, respiration rate. Then what I find actually is a simple linear classifier can perfectly separate walking and running. So here deep learning is doing nothing magical. It's doing indirectly and expensively what people have been doing for decades directly. And it's attributing its success to some kind of magical thing that's happened here. There really is no magic. So I actually believe that most deep learning papers for TSAD are like the examples on the last page. They're using a very complex method to solve a problem that could have been solved decades ago with much, much simpler methods. And they're kind of waving their hands and attributing their success to some kind of vague magic of deep learning. But they should really attribute to the fact that the datasets they're working on are incredibly trivial, as we've already seen. Before I move on, other folks have actually pointed out something very similar in slightly different contexts. Here are 2 papers that show that classic algorithms are just as good or better for deep learning algorithms in various time series contexts. So while deep learning is a big offender here, I want to make a more general point. Most papers in TSAD have what I call unjustified complexity. They're introducing models that are far too complex to be actually useful. So recall the New York taxi example dataset that we've seen before. Up to the limit of subjectivity of labels, it's pretty clear we can find all the anomalies with a very simple 20-year-old single parameter method that takes 10 lines of code. And yet there are many, many papers that try and solve this problem and do as good or maybe worse, but in doing so have to set 5 or 6 or 7 or 10 parameters. And the question is, what does that actually achieve? Here's an example of a paper that's just Byzantine in complexity. It's adaptive somehow, it's hierarchical somehow, it does multi-anomaly detection, It has adaptive model selection. It uses a contextual bandit problem. It uses reinforcement learning, and so on and so forth. I literally could not count all the parameters that were set in this paper, but it's clearly well more than a dozen. At the end of the day, to evaluate this, they say, we look at this data set here, and we label an anomaly if it has a weekday with low power consumption. Now, again, it's a nicely written paper, but at the end of the day, we could do this 20 years ago with 10 lines of code, as I'm shown here. So what have we actually achieved with this complicated method? My final criticism of papers in TSAD is many of them claim to do anomaly detection, but they're actually not. So it's common in papers to see sentences like this one here. We manually label a day as abnormal if it is a weekday with low power consumption, and so forth. But think about this. If you can concretely define in a single English sentence what you expect to find, is that actually anomaly detection at all? Anomaly detection is meant to be essentially expected unexpected. But for these examples above, I could actually just do similarity search, which is a much, much easier problem. So far, this talk has been quite negative, so I want to end on a more positive note. I've created a set of benchmark data sets that I hope actually will help us do a little bit better in this space. So these data sets actually largely solve the mislabeling problem we discussed, and they completely solve the triviality, run to failure, and unrealistic density problems we mentioned. And they actually also solve the spurious precision problem. So I'm not going to show you all 250 data sets, but let me show you one or two to get a flavor of what we're doing here. So first of all, the format. The time series are one continuous long time series. And the first section, obviously, is the training section. And then we have a test section. And the test section, there's exactly one anomaly. And we also have all the metadata that explains where the anomaly came from, exactly where it is, how long it is, and so on and so forth. So you might ask, how can I be sure there's exactly one anomaly in the test data? And here's an example how I did it in one case. So here I had a data set that has the left foot and right foot walking on the force plate. As it happens, the left foot data is corrupted, but the right foot data is okay. So what I did was, I took a single beat, if you like, from the left foot, and I carefully grafted it in to the right foot data set. So this means that the entire data set is normal, except for that one anomalous beat. So let me finish up. As I hope I've convinced you today, the vast majority of papers in TSAD make no contributions. In the absolute best case, they're solving problems a hard way that could have been solved in an easy way 20 or 40 or 50 years ago. In the worst case, they're actually contriving experiments and cherry-picking data sets to make an intrinsically bad idea look better than it really is. We should actually see these facts as an opportunity. It's an opportunity to have much more introspection as a researcher. We need to actually think about the problems. What are we trying to do? We need to think about evaluation. What really counts as evidence of success for these problems? We should also be much more critical as reviewers, but only in a constructive way, of course. First of all, we should absolutely demand 100% reproducibility. All code, all annotated data, all parameters, all seeds at review time. We should insist that people test on common sense, simple benchmarks. You're going to be amazed how often those are very, very successful. And then finally, most of the problems, as I mentioned at the beginning of this talk, really come down to the paucity of good data sets. And so we should reward people who will take the time and effort to do all the hard work of making good data sets and making them public. Thank you for watching my talk. If you have any questions, comments, criticisms, I would love to hear them. Please feel free to email me. The datasets I mentioned are available on a link from this website here. Thank you.